Okay, so we've answered the question, how much energy do we use and where does it get used? Now we're going to answer the question, where does all that energy come from? Thus far, we've been talking about the 7.8 exajoules of energy that gets used or consumed in Canada. We're going to talk a little bit about the breakdown of that. You can see there's about 2 exajoules of electricity, 2.4 of natural gas, 3.2 of refined petroleum, and about zero point 0.1 exajoule of natural gas liquids. But of course, that's just what arrives to the end user. Upstream, there's significantly more energy that's produced in Canada, about 16.6 exajoules. Where does the difference lie? Well, exports, some imports. Then, of course, thermal power plants burn some of this coal to make electricity or burn some natural gas to make electricity. And then some of that energy just gets converted to thermal energy. Then, of course, energy is used to operate pipelines and to provide lights for power plants, etc. And then some of this petroleum that is pulled out of the ground is used as feedstock for the plastics industry, for instance. So that's how we go from 16.6 exajoules down to 7.8 exajoules in total for the country. Now that's 7.8 exajoules divided by 12.99 million residences. Let's just remind ourselves that an exajoule is times 10 to the power of 18 joules. And if we divide that by our 12.99 million residences, that's how we get our 6 times 10 to the 11 joules, which is 600 times 10 to the 9 joules, which is 600 gigajoules per residence per year. Now, the breakdown of this 7.8 exajoules, and thus the average breakdown per residence, can be expressed as a percentage. These percentages, of course, just come from the previous chart. So we see 2 of electricity divided by 7.8 exajoules. That's where this electricity of 26% comes from. Similarly for natural gas and petroleum. Notice the preponderance of fossil fuels, even in Canada, hydroelectricity is superpower. We still have 74%, nearly 80% of our energy that comes from fossil fuels. And it's even more than that because under electricity, well, yes, we've got hydro, yes, we've got nuclear, but the next one down there is coal, because quite a few provinces still use coal for their electricity. So I believe that's about 2 or 4%. Maybe 4% for coal, although that number is going down over time. So really you need to add this 4% to these other two to get the total. So that takes us up from 74 to 78, nearly 80%. And that is the world average. Now, there's 2 problems with fossil fuels. First of all, we may be running out. We may be reaching a peak of production in the face of growing global demand, and production might not be increasing. We are still producing massive amounts of petroleum and finding massive amounts of petroleum, but there's a question of whether supply is going to keep up with demand. The other issue, of course, is the burning of fossil fuels releases ancient carbon into the atmosphere, carbons that have been sequestered underground for millions of years, and this may be having an impact on our climate. So as a result, we're interested in providing energy to society using renewable energy resources. So these are things like wind energy and solar, etc. Now, one of the most exploited renewable in the world is hydro, and we're really lucky to have a wealth of hydro resources, and it contributes significantly to our energy picture. The others, as of yet, don't. Wind power is maybe 1%. Solar is even less. There's not a lot of those at present in Canada. So let's talk a bit about hydro. Let's imagine we have a dam here, and the water's on this side. And then there's the penstock, which carries water down here to the powerhouse, where they make the electricity. And we just want to say if this is 80 meters of drop, that's the head or the vertical drop, and a flow rate of 2,500 kilograms per second, how much power can you make with that? So a kilogram is basically a liter, so this is 2,500 liters per second. And so that's probably the easy way to approach this is to realize that we're dealing with a transformation from gravitational potential energy to electrical energy. So how much potential energy do we have? Well, potential energy is mgh. We divide that by time. So the mass is 2,500 kilograms for 1 second. The gravity field is 9.8 newtons for every kilogram. And then the height is 80 meters. Now, if you work that out, that's 1.96 times 10 to the 6 joules per second, or 1.96 megawatts. Now, that's just the rate of height energy, but generators, electrical generators anyway, are remarkably efficient. So the energy output, which will be electrical, is 90% of the energy input, which is the potential energy. So if you solve that for the output of your generator, it's the 90% of the PE. It's 0.9 times the 1.96 megajoules each second. And that works out to be 1.96 times 0.9, 1.76 megawatts. So, the great thing about hydropower is, as we'll see in one of our lab activities, that it can follow demand. So you can allow a bit more water through, make a bit more electricity. This is not the case with, say, coal or nuclear power, because those generators, those boilers to make steam, you've got to get it in a sweet spot where it's efficient, and then you can make power at that point at about, say, 30% efficiency. But if you're trying to produce less steam by turning the heat on or up, the amount of coal, your efficiency goes way down. So these thermal power plants, you turn them on, you tend to leave them on. Of course, the downside of hydro is you can't just plunk a new power plant anywhere, and we've already dammed a lot of the rivers in Canada, so there is perhaps a restriction on future potential, but there's still a lot of future potential in Canada and around the world. Let's look at a relationship now that's going to be useful for studying the power of wind generators. We're going to find the amount of wind energy that impinges on a turbine. First of all, the mass. Since density is a ratio of mass to volume, we know that mass will be the product of density and volume. Now, by volume, we're going to refer to the volume of air that's going to strike the turbine blades in a given amount of time. Well, that air volume is going to be a cylinder of air, okay? And that's the air that's going to impinge on the turbines. So the volume of a cylinder is the base area times the height. So that's pi r squared for the area of the circle. And the radius of the circle is exactly the same as the length of the turbine blades, because these things sweep out a circle. And it's that circle there that's the same as the size of the wind cylinder that's going to strike it. And then multiply that by the length of that cylinder. Well, that length is just equal to the wind speed times multiplied by the time of interest. So there's an expression for the volume of the air that's going to strike our wind turbine. Well, we just did that derivation. Okay, so because velocity is distance over time, a distance is velocity times time, so a length is vt. Okay, so Oh, I'm really jumping ahead of myself here. So yeah, so the volume then is going to equal the product of pi r squared and Vt. We had written that on the previous page. Because it's pi r squared times the length, but the length is Vt. And the mass, of course, is going to equal the density times the volume. So that's density times pi. Yeah, what a mess. So this is pi r squared Vt. This is density times pi r squared Vt. So that's the mass, density times volume. And now the kinetic energy is 1/2 mv squared. So this is the mass, so we put this in for mass, and then we multiply by v squared. So now we've got the amount of wind kinetic. Now, typically, well, let's simplify that a little bit first. So there's going to be a factor of 1/2, and then there's rho, the density of the air. There's pi. There is the square of the radius. Then there is the cube of the speed, and then a factor of time. Okay, so about 90% of that will be captured. And so we get a term here involving the efficiency. So efficiency comes in rho pi r squared v cubed t. And then the power, we just take this energy and divide by time. And so the time just disappears. And we end up with something that depends on the square of the radius. So obviously you want to make nice long turbine blades. And also the cube of the velocity. So that means that the velocity of the wind in that vicinity is critical. Now, earlier on in the course, you'll recall we took a trip up to Grouse Mountain. And up on Grouse Mountain, this wind speed was very small. Oops, what happened there? And because the wind speed's very small, they don't make very much electricity up there. Now we worked out the load factor, which was the actual power that we produced over the maximum power. That's actually one of your homework problems. And you could think of that as the percentage of the time it's producing at full power equivalent. For Grouse Mountain, it was less than 1%. So that means it produces in that location 1% of what an optimally placed turbine would produce. No, that's not true. 1% of the total ideal rating. But even the best turbine placement in the world, the wind doesn't blow all the time. So for wind, your optimal load factor is probably 30. Realistically, in most placements, it's probably 20. That's, would be a typical load factor. So if you found a really good place, you're probably going to make 20% of the nameplate power of the rating of the turbine. Grouse Mountain, obviously, you're making a lot less than that. So the load factor is a critical variable in assessing the amount of power that you can expect from a given installation. So let's say we've got a turbine in a really good place. So you've got 10 meters per second of wind speed, which is pretty good, 30-meter long blades, and a 90% efficient turbine. So we'll just use the relationship that we just derived. So that was a factor of 1/2, and there was efficiency, density of the air, pi r squared, and then cube of the velocity. So we're told the efficiency was 90%. The density of the air is 1.29 kilograms per every cubic meter. We have 30-meter long blades, and then we have a 10 meter per second wind. Now, dimensionally, meter squared cancels off this meter. then you get this meter cubed, so you end up with meters squared, and a kilogram also up there, and then you end up with per second squared per second. Now a kilogram meters squared per second squared, that's a joule, and then if you divide that by a second, it's a watt. So we end up with watts of power here. And let's see just how much power that is. So it's 0.5 times 0.9 times 1.29 times pi times 30 squared times 10 cubed. And that is 6 powers of 10. So that is 1.64 megawatts. So that's about the nameplate rating on the Grouse Mountain model. But of course, the Grouse Mountain doesn't make power at that rate very much. Only 1% of the time is it making power at that rate, just because the wind speed's so low. But in a good location, a 10 meter per second wind, steady 10 meter per second wind, you can make 1.64 megawatts of power.